So let us begin our today's session. Any queries with regard to the previous session? There we have started vector spaces, and I have given the basic definitions of what is a vector space, subspace, linear combination, linear span, etc. And we have taken occasionally one or two problems on it. So do you have any queries on that session? Say. Yes or no? If you don't have any questions, let us begin with the other part. Shall I continue then? Right. So earlier we have discussed about the subspaces. A subspace is nothing but whenever you take a vector space V, if you take a subset in it, this subset we are calling it as subspace, where it is a subset of V and it itself becomes a vector space. Please understand that the concept of vector spaces is very abstract, similar to the regular numbers, polynomials, matrices, and anything you can take. So whenever a set satisfies these specific conditions, we are calling it as a vector space. So whenever we utter a result or a theorem, it is not only applicable to numbers, it is applicable to every set which satisfies the specific properties given earlier. Now, what happened to if you consider the intersection of subspaces and if you consider the union of subspaces? And whenever we know that a subspace is given, apart from verifying all the 9 conditions to say that it is a vector space or subspace, we simply verify for 2 test conditions. In test 2, we verify the condition for A alpha plus B beta, the necessary and sufficient condition. In test 1, we verify for 2 conditions, that is alpha minus beta belongs to W and A alpha belongs to W. Apart from verifying the 9, these are enough to check the criteria of a subspace. Now let us deal with the case of intersection. Suppose I have taken 2 subspaces W1 and W2. Now my intention is the intersection a subspace or not? And the result is yes. And let us prove for it. So intersection is nothing but the common part for the 2 sets. Since every subspace contains the 0 vector that is default, we can say 0 vector belongs to W1 and 0 vector belongs to W2. Hence 0 vector belongs to the intersection. So always intersection is a non-empty set. Now to prove that it is a subspace, let us take the test condition A alpha plus B beta. If I am proved that A alpha plus B beta belongs to the intersection, it becomes the subspace. So for this, you take any 2 vectors in the field and any 2 scalars in the field and any 2 vectors in the intersection. So this implies that we can say alpha comma beta belongs to W1 and alpha comma beta belongs to W2. Since these are subspaces, we can say that A alpha plus B beta belongs to W1, A alpha plus B beta belongs to W2, because W1 is a subspace and W2 is a subspace. So from this we say that A alpha plus B beta will belong to this intersection. Hence, by the necessary and sufficient condition, W1 intersection W2 is nothing but a subspace. So in this way you prove the result. Occasionally there are so many results for it which are theoretical. This is also one of the theoretical results. With the examination point of view, there is no need to study for it, but if you understand the logic how we are going to prove a result, then the tactics is very familiar with you, right? So you can extend this type of context to n number of sets. So you can prove that W1 intersection W2 intersection W3 is a subspace. Similarly, you take n sets W1, W2, so on, Wn. You take n subspaces, you consider all the common intersection. This intersection is again a subspace of the vector space V using the same logic as stated now. Here I have written for 2 sets, there you will write for n sets. That's it. So is the concept clear? So what is the point we have learned here? The intersection of subspaces is a subspace. You can take any number of intersections, 2 intersection, 3 intersection and so on, n intersection of subspaces. Okay? If you have any doubts, you can ask. If you are clear, I go to the next part. Is it difficult or comfortable for understanding? All right. So let us take the case of union of subspaces. Is the union always an intersection or not? For this, the result is no. Specifically, need not be. Whenever you consider union of subspaces, it need not be a subspace again. For this, let us take a small example that you take W1 as all 3D points of the form So from this, what we can say about W1 on observing the pattern of the points? W1 is nothing but y-axis. Agreed? Yes or no? So, if you take W2 as of the form, it is nothing but z-axis. So, if you consider the union, it is nothing but points of either of the first form or of the second form. Agreed? Because you are taking the union. Union is nothing but whatever the point you consider, it will be either of the form this or of the form this. Accepted? right? So you can say like this. Now I am saying that this union need not be a subspace or it is not a subspace. For example, let us take a small counter example. Just take a point and another point. So this is a vector belong to the union and this is a vector belong to the union. Now just apply the closure law. If you add them up, you will get the point as 0, 1, 5. So will it belong to the union? Yes or no? Is it right or wrong? All of you agree? Yes. So what happened here? Alpha belongs to the union. We confirm that. Beta belongs to the union. We confirm that. But alpha plus beta does not belong to the union because the result is neither of the forms, either the form 1 or form 2. You cannot confirm that the vector belongs to that set. So union need not be a subspace always. That we should take trivially. But union is a non-empty set. Always the zero vector origin 0, 0, 0 belong to the union. So union is a non-empty set, but it need not be a subspace. So from this, one interesting observation we can deduce that in the next level. If you want to say that a union is subspace, what must be the checking condition? In other words, if you want to make the union as a subspace, what is the pattern of those sets? Are you getting the point? Say. So, one interesting result developed here is whenever you have two subspaces, if you want to say that the union is a subspace, it is possible if and only if in the two sets one must be a subset of the other. So if you want to confirm or say the union is a subspace, the confirm condition or the checking condition is one set must be a subset of the other. In that case only the union is always a subspace. Now let us prove it theoretically. So shall I go? Right. So if you observe the result, it contains two parts. By assuming this, you should prove this one. Similarly, by assuming this, you should prove this one. So I just want to move from the other side first. So let us assume that W1 is a subset of W2 or W2 is a subset of W1. Let us assume that. Please understand, basically I have taken that W1 and W2 are subspaces. Please understand that. So my intention is the union a subspace or not? So if you take the first case, if you observe that W1 is subset of W2 means this is the smaller one contained in W2. So if you calculate the union, what will be the result? Can you say? If I say that A is a subset of B, what will be A union B? Are you getting the idea? Let us have a small example. So you agree that W1 subset of W2 accepted? Yes or no? Right. So from this, if you calculate the union, what is the result? Is it W1 or W2? W2. So it means that whenever you take a subset pattern, the bigger one is nothing but the union. So here you will get that this is nothing but W2. So if the sets or subspaces what you have taken are such that W2 subset of W1, then in this case the union is nothing but W1 because this is the bigger one. So from our assumption, either this is subset of this or this is subset of this. Whatever the case you choose, these two are equal. Since this is a subspace, automatically it will become a subspace because these two are equal. Since this is a subspace, these two are equal, hence the union is a subspace. So whatever the case you consider, the union is a subspace by default. Clear? Yes or no? Are you getting the point? Right. Now, one part is clear. Let us go with the other hand. So, what we are going to prove? We are supposing that union is a subspace. And what we are going to prove? Either W1 subset of W2 or W2 subset of W1. We are going to prove this condition. Since there is no direct proof available, let us prove it in the contradictory way. So what does it mean? I assume that this condition is not correct. Then we start a procedure. We will get a contradiction. What is meant by contradiction? A result which is not perfect practically. So, since you are ending up with a contradiction, our supposition is wrong. Hence, obviously, the claim must be hold. Okay? Is the approach clear to all in proving it? Right. So, what we are supposing, if possible, suppose W1 is not a subset of W2 and W2 is not a subset of W1. We have to prove this one. Since there is no direct proof available, I am proving in the other way. Now I start the procedure, I will get a contradiction. This is my assumption. So from this, we can visualize the sets like this. Say, W1 is equal to 1, 2, 3. W2 is equal to 1, 2, 4. Or you can take 5 also. Now see, from this, can you say that W1 is a subset of W2? Yes or no? Is W2 a subset of W1? Yes or no? No. So from this we can understand that since W1 is not a subset of W2, you can find at least one element which is exclusively belong to W1 and which will not be there in W2. Similarly, for W2 also, you can find at least one element which is not there in W1 because these are not subsets to one another. So you can have the picture like this. You can say, let us take that there is an element X which belongs to W1 only, which is not there in W2. Similarly, exclusively you can find an element Y in W2 such that Y does not belong to W1. But understand that these X and Y will belong to the union. Accepted? Yes or no? If you take any element in one set, that is by default belong to the whole union. So you can say that X and Y will belong to the union. From our supposition, the union is a subspace. So it is a vector space. It will satisfy all the properties, closure, associative, identity, etc., etc. It will satisfy all the properties. Now, from closure law or closure property, you can say that if you add the two vectors, the result will belong to the set. So I am saying that X is a value, Y is a value, both will belong to the union. Since union is a subspace, if you add them up, the result also belong to the union because it is a subspace. So the result must belong to the either of the sets. Agreed? The result must belong to the either of the sets. So if you add X and Y, the result is X plus Y. That must belong to either W1 or W2. Accepted? All of you agree or any questions for anyone? Fine. So you have two possibilities here. So one, X plus Y belongs to W1 because whenever you say that an element is there in the union, so the element must belong to one of the sets in that union. Otherwise it cannot be there. So the other possibility is it may belong to W2. So let us take the first case. Now I have two values in W1, X and X plus Y. Please understand, whenever you have taken that a subspace, it always satisfies the necessary and sufficient conditions. So since I am taking that W1 union W2 is a subspace, W1 is a subspace, W2 is a subspace, all these sets will satisfy the condition A alpha plus B beta belongs to that set. So since A alpha plus B beta belongs to W1, alpha beta are vectors, A comma B are numbers. So I will say that alpha as X, beta as X plus Y. And I can take any kind of numbers. So I will take A as -1, B as 1. So A alpha plus B beta must belong to W1. So from this, Y must belong to W1. Is this correct? Did you get the concept here? How I have applied the condition? Right. Is Y belongs to W1? Do you agree? So this is a contradiction, right? Right. Similarly, you go with the same case here. So X plus Y should not be here. You take that X plus Y belongs to this set. Again, you apply the condition. So you take that alpha and beta values as alpha as X plus Y, beta as Y, right? You take B as -1, you take A as 1. So A alpha plus B beta. So from this you can say that X belongs to W2. Is this correct? No, because X will belong to W1 only exclusively. So whatever the choice you are making, you are getting a contradiction always. So why this contradiction is arrived? Because earlier you have started with that W1 is not a subset of W2 and W2 is not a subset of W1. So our supposition is not correct. So the claim must be hold. So either W1 subset of W2 or W2 subset of W1 must hold. So in this way we prove the result. Any questions to anyone? So these two results, why I have taken that, I think these are given earlier in UPSC papers, that's why I have discussed it. Otherwise, I will never go with discussing the results. So any questions for anybody with regard to this problem? The result? Is the result clear for everyone? Any doubts? Right. So let us take some definitions here. Linear dependence and independence. These two definitions are very important with regard to problematic view as well as exam perspective. So let us take a small example which will give an idea for you. So this is the vector 1, 2. Now I am taking another vector 2, 4. So is this point lie on this vector or not? In other words, these two values belong to the same line or not? Yes or no? All of you agree? Because if you extend this, 2, 4 will be here. So you can say that accepted? Right. Now from this you can say that do you agree for this relation? Right. Now let us give some numbers or some names. So you made a relation here like that. Am I correct in writing that using the names? So in the previous class, I have given a definition that linear combination what is meant by linear combination? The sum of the products, we are calling it as a linear combination. Whenever you multiply a vector with a number and take those sums, it is called linear combination. If I have simply taken a set alpha, beta, gamma, the linear combination is nothing but a1 alpha plus a2 beta plus a3 gamma, where a1, a2, a3 are nothing but any numbers you can take in the field. So if you observe that here the vectors alpha and beta are linearly dependent, so you can write that you can have a linear combination. The result of the linear combination is 0, and in that linear combination scalars are possibly non-zero. So what is the definition of linear dependence? If you write theoretically, whenever you took a set of vectors alpha 1, alpha 2, so on alpha n, we say that the set is linearly dependent if whenever you take a linear combination whose result is 0, then the scalars must be non-zero. That is, at least some scalars are non-zero. Clear? So what is the definition of linear dependence? Whenever you take a set of vectors, say alpha 1, alpha 2, so on alpha n, we say that the set is linearly dependent. Whenever you take a linear combination using the set of vectors, the result of the combination is 0, then in that combination, whatever the scalars you consider, there must be some non-zero scalars. So, in other words, you can say that it is possible to find some non-zero scalars so that the result of the combination is 0. Okay? Is the definition clear? Any questions? Right. So linear independence means whenever you take the linear combination as 0, all the scalars are 0. So if you write a linear combination, the result is 0, then all the scalars must become 0. In other words, by taking a1, a2, so on an, all these numbers as 0, then only the result of the combination will become 0. It is called linear independence. In a simple example, you can visualize the picture as, let us take x-axis, let us take y-axis. So these two are linearly independent. Don't feel that I am taking the perpendicular case. So these two are independent, because if you take any vector here, the linear combination is 0 only whenever you take the scalars are 0. For example, if you take the vector as 2, 0, 0, let me say. If you take the vector here as 0, 1, 0. So if you want to write so the result will be 0 only when A and B becomes 0. Otherwise, this is not possible to get 0. Accepted? Except 0 in place of A and B. If you take any value in place of A or B, the result will not be equal to 0. Agreed? So, linear combination is nothing but linear independence of a set is nothing but whenever you take a set of vectors, the combination will become equal to 0 only when the scalars in that combination are completely 0. Clear? So this is called about linear dependence and independence. Please understand that we are calling dependence or independence based on the scalars. So by the choice of scalars only, we are saying that the set is dependent or the set is independent. So usually scalars belongs to which set? Field. So depending upon the field, we say that these set of vectors are dependent on this field. These set of vectors are dependent on this field, independent on this field. We say like that. So dependency and independency is based on the scalars and the field, not on the vectors we have taken. Okay? Let us take one small example which will give you a good idea. So from this result also you can observe that whenever you take a set having only two vectors, if you say that the set is linearly dependent, then among the two vectors, one vector is a multiple of the other. So a scalar multiple of the other. So if I say that I have taken a set which consists of only two vectors, alpha, beta, then if I have mentioned that this set is linearly dependent, immediately we can say that alpha is equal to some number into beta or beta is equal to some number into alpha. Okay? Clear? Please take a note of this one. Now, I am taking a small example that I took a set having 1 is a vector and I is another vector. Please understand that I have taken one-dimensional vectors where there is only one coordinate is there. This is one vector and this is one vector. Now, I can write that I can write that 1 is equal to minus I into I. Accepted? So I have written one vector as a multiple of the other vector. So this set is nothing but linearly dependent. Now the question is, the set is linearly dependent on what? What field? Now understand that here the scalar is I. Is it a real number or complex number? Complex number. So the given set is linearly dependent on the vectors over the complex field, and this set is linearly independent on the vectors over the real field, because it is possible to represent one vector as a multiple of the other, but the scalar which is available does not belong to the real number field. So if you take the real number system, these two are independent. You cannot write one value as a multiple of the other. But if you take the complex number field, here it is possible to write one value as multiple of the other, so it is dependent here. Now, did you get the exact meaning of dependence based on field, how we are mentioning? That's it. Are you clear with this example? Right. Now, after this, let us take one or two small problems on it, linear dependence and independence. Before that, I just want to give some results which are useful while proving the good number of problems. Suppose I have an LD set. Then, if you take any superset of it, so all these are LD. So what is the first result? Every superset of LD set is LD. That is one result. Now I have taken an Li set, linearly independent set. So if you take any subset for it, any subset, all these are Li. So what is the second result? Every subset of linearly independent set is linearly independent. Now the third result is if you take a set of vectors, if the vector set contains a zero vector, then it is LD. It is very simple result to understand. Let us have a small example. This is my set of vectors. Alpha is a vector, beta is a vector, gamma is a vector, and I have included zero vector also here. Since zero vector is presented in this set, it is LD. How it becomes LD? It satisfies the definition. How? You can write the linear combination as 0 into alpha, 0 into beta, 0 into gamma, and any number a into 0 bar, but the result is 0. Now see, I have written a linear combination. The result of the linear combination is 0, and in which I got one non-zero scalar. So it satisfies the definition of linear dependence. Therefore, the set is LD. So whenever I have given a set of vectors, then if you want to check whether it is LD or not, very simple, just check that it contains a zero vector or not. It is a simple check. If it contains a zero vector, it is LD set. Okay. So from this perspective, we can say that whenever you mentioned about a independent set, all the vectors are non-zero. If I have mentioned that it is a linearly independent set, all those vectors in that set are non-zero vectors. Okay. And one final result is, I can say two more results. If you take only one vector in the set and it is a non-zero vector, then it is Li. It means that a singleton set is linearly independent. That means a set having only one non-zero vector is linearly independent. And while proving the problems, one good result is there, that how to check whether a set is linearly dependent or not. Suppose I have taken a set of vectors like this, alpha 1, alpha 2, so on, alpha n. Now, if this set is LD, then you can find at least one vector in that set which is a linear combination of the preceding vectors. So it means that, let me say alpha 1, alpha 2, so on, alpha 10. I have taken 10 vectors in one set and I mentioned that it is LD. So among these 10 vectors, right from second vector onwards, you can find at least one vector which is a linear combination of preceding vectors. Let me say it is alpha 5. It means that you can write alpha 5 as some number into alpha 1 plus, some number into alpha 2 plus, some number into alpha 3 plus, some number into alpha 4. So alpha 1, alpha 2, alpha 3, alpha 4 are preceding vectors. So you can write alpha 5 as a linear combination of preceding vectors. So it is an if and only if condition, you can say. Right? So if we say that the set is LD, you can find at least one vector which is a linear combination of preceding vectors. Is the point clear? Any questions to anyone? Please tell. Are you clear with this? Fine. Is my voice audible to all and you are getting the data without any interruption through internet? Because I am getting a little response from your side, I have a doubt whether you are stuck with the concept or the net speed is slow. I am not getting actually. Can you elaborate? Are you comfortable while understanding this concept or feeling different? Say. Okay. Now let us take a problem. So here I have taken three vectors, 1, 3, 2, 1, minus 7, minus 8, 2, 1, minus 1. So the question is, we have to prove that the set is linearly dependent. So let us go with the definition. So what is the definition? If we have written a linear combination for the given set and the result is 0, 0 vector, it means then it is possible to find non-zero scalars. So let us write the linear combination first. Here the field is real field, real numbers are there as scalars. So let us take that A into 1, 3, 2 plus B into 1 minus 7 minus 8 plus C into 2, 1 minus 1 is equal to 0 vector. So if I am able to find non-zero values for ABC, then I am done, because linear combination is giving 0 for me and I can find non-zero values in place of ABC. So it satisfies the definition of linear dependence. Therefore, given set is LD. Now let us write the corresponding equations here. If you have written that A, 3A, 2A, B minus 7B minus 8B, 2C, C minus C is equal to 0, 0, 0. So if you add them, the respective values, the result is nothing but A plus B plus 2C equal to 0, 3A minus 7B plus C equal to 0, 2A minus 8B minus C equal to 0. So solving the above equations, I should mention that I can find non-zero values for ABC. In other words, I can allocate non-zero values for ABC so that all the three equations will get satisfied. Now what is the procedure? Can you specify how to do? How to solve those equations? Are you getting it or not? This is nothing but system of equations. Accepted? And it is a homogeneous system. Right side values are 0. So how do we solve a homogeneous system? Take the coefficient matrix, apply the row operations, reduce that into echelon form, and based on echelon form, we will find trivial solution, infinite number of solutions. Whatever the possible case, we will mention that. So let us write the coefficient matrix here. So 1, 1, 2, 3, minus 7, 1, 2, minus 8, minus 1. So if you apply the row operations, R2 tends to R2 minus 3R1, R3 tends to R3 minus 2R1 will be equivalent to 1, 1, 2, 0, 0. R2 minus 3R1, so minus 10. Minus 5. Here R3 minus 2R1 minus 10 minus 5. So from this you can say R3 tends to R3 minus 2R2, and you can say R2 tends to minus 1 by 5 R2, which is equivalent to 1, 1, 2, 0, 2, 1, 0, 0, 0. Accepted with the operations. So what is the rank of the matrix 2? So we can say that So these are the values of ABC. Agreed? Any questions? I think you should take -3 there. Accepted now? The values of ABC. Can you recollect the procedure for solving homogeneous equations? Now, if you put that k is a parameter, you can take that k is equal to 2. From this, you can say that a is equal to -3, b is equal to -1, c is equal to 2. In other words, you can say that a is equal to 3, b is equal to 1, c is equal to -2. So, if you substitute these values in the equations, they will get satisfied. So, you have found non-zero scalars ABC such that the result of the combination is 0. Therefore, the given set is linearly dependent set. Fine. So, this is the way we solve the problems. Are you clear with this? The method, right? Then let us take the other one. This thing you can do on your own. I will give 2 minutes time. You solve it and tell me whether it is linearly dependent or not. So the set of vectors I am giving to you are 1, 2, 0, 0, 3, 1, -1, 0, 1. So are they linearly dependent or independent? You please check and tell. Take a minute of time and solve it. If anybody has any doubt with regard to the approach, you can ask. I will give the hint for you. So you are getting non-zero vectors and you are saying that it is linearly dependent. You are getting non-zero scalars there. Yeah. So let us go for it. So let us apply the row operations there. So R3 tends to R3 plus R1. Again, you can say that R3 tends to am I correct in applying the operations? Say. Okay, that's right. So there you got a problem. So here the rank of the matrix is nothing but 3. Therefore, it has trivial solution. So trivial solution is nothing but 0 solution. So whenever you take ABC as 0, then only the 3 equations will get satisfied. Otherwise, you won't get a possible solution for it. Okay. So from this perspective, whatever the number of equations are given for us, we simply go with the matrix and calculate the rank. So what happens here, if the rank is equal to number of variables, then the homogeneous system will have trivial solution. So the scalars are nothing but 0 only. So the given set of vectors will become linearly independent. So if you say that the system is dependent, then always rank will be less than number of variables. So that you can take some constants there among A, B, C, D, the variables, the scalar values. So you can find some non-zero values for the scalars A, B, C, so that the system will become dependent. This was the whole approach. Any questions to anyone? Now let us take the problem, which is also useful to you. So is everyone clear with that solution? Any questions for anyone? Right. So let us take that. Alpha, beta, gamma. This is a Li set. Now, I want to check that if you sum them, so I have given 3 vectors, alpha, beta, gamma, and I am saying that the 3 vectors are linearly independent. Now the question is, you need to check whether the sum of the values alpha plus beta, beta plus gamma, gamma plus alpha, the 3 new vectors are the Li or not. So how we are going to prove? Take the usual definition. So let us take that A, B, C are nothing but the scalars, such that the linear combination is 0. Now, you can separate all the values, you can multiply all the things. So if you common A, you can take one more step. So from this you can say that if you take alpha as common, A plus C into alpha plus A plus B into beta plus B plus C into gamma is equal to 0 bar. Accepted? Since alpha, beta, gamma is a independent set, so whenever you write a linear combination using this set and the combination is 0, then the scalars in that combination must be 0 because it is the independent set. From the definition it follows. So A plus C is equal to 0, A plus B is equal to 0, B plus C is equal to 0 as alpha, beta, gamma or Li. So using these relations, I should prove the scalars what I have taken are 0. If I am able to prove that since all the scalars became 0, this set becomes Li. If among A, B, C at least one value is non-zero, this set becomes LD. Right? Now, how to solve this? Let us write this system in the form of a matrix. So 1, 0, 1, 1, 1, 0, 0, 1, 1 of ABC. So you can apply R2 tends to R2 minus R1, R3 tends to R3 minus R2, etc., etc. you can convert into echelon form, you cannot get a 0 row in the last place. So here, the rank of the matrix is 3. So which is equal to number of variables. So the given system has only trivial solution. So you can say only A, B, C values are 0. Then only the system will get satisfied. Therefore, this set is linearly independent. That is the conclusion. Okay. So please check on the solution. Any doubts or questions to anyone? Fine. So this is the new problem. Easy to understand. So let us take that. I will take 4 vectors. Now see, I am saying that if I take all the 4 vectors as in one set, then it becomes LD. Or if I take or if I choose any 3 of the 4 vectors, it becomes Li. So this is my objective to prove. So let us go with the first one. So I have considered all the 4 vectors in one set, and I am going to prove that it is LD. How? Let us take the definition as it is. So take the scalars A, B, C, D. Such that the result is 0 vector. Now you need to show you can find non-zero values for A, B, C, D. So if you simplify the part, it is nothing but A plus D, B plus D, C plus D is equal to 0, 0, 0. So please check on that simplification. Agreed? Right. So making the coordinates equal to 0, you will say A is equal to minus D, B is equal to minus D, and C is equal to minus D. So at this point we can say that the given set is LD. How? If I take D is equal to 1, what are the values of ABC? Minus 1, minus 1, minus 1. If I say D is equal to 10, what are the values of ABC? Minus 10, minus 10, minus 10. So I can find non-zero numbers ABCD such that the combination is 0. Therefore, the given 4 vectors are LD. Any doubts? Say. Is that clear? Fine. Now the second part of the question is, if you take any 3 of the 4 vectors, the set is independent. So let us go with it. So any 3 of the 4 means you can have choices. So what are the possible choices here? You can take alpha, beta, gamma together as one set, alpha, beta, delta as one set, beta, gamma, delta as one set, and alpha, gamma, delta as one set. So can you say any other possibilities are there for the selection of any three of the four? So these are the only possibilities. So we need to show all these are linearly independent sets. So how do we do? Among these things, you can pick up one, prove it Li. Similarly, we can prove that the remaining sets are also Li. So for the question tag, among these four choices, we start with one choice. We prove that it is independent set, and we mentioned that similarly we can prove other sets are also independent. Okay. Now you tell me 1, 2, 3, 4 among the four choices, which choice you want me to take? Third one. So our task is we need to show this is Li. So let us write the combination first. So A into 0, 1, 0 plus B into 0, 0, 1 plus C into 1, 1, 1 is equal to 0 vector. So beta, gamma, delta. So if you sum up that, it will be C, A plus C, B plus C is equal to 0, 0, 0. Now from this, C is equal to 0, A plus C is equal to 0, B plus C is equal to 0. So which obviously gives that A is equal to 0 and B is equal to 0, as C is 0. Accepted? Therefore, all the scalars in that combination is 0. Therefore, it is Li. In the similar way, we prove for the remaining three also. That's it. Fine. Right. Now, let me take one more thing. From that I will conclude. I will give the hint for you how to solve it. Now, my question is, if I took all the three matrices into one set, is it Li or not? So how can I prove? Please understand, vector spaces concepts and definitions are applicable to all type of sets. Matrices, polynomials, functions, numbers, points, everything you can apply. So if you know the definition fundamentally in a correct way, you can do any kind of problem very easily, no difficulty at all. So let us write the linear combination first. You take any scalars ABC such that linear combination So what is meant by 0 bar here? Nothing but the 0 matrix. So given ABC are 2 by 3 matrices, here 0 bar is nothing but 2 by 3 matrix, 0 matrix. So if you have written that A into 2, 1, minus 1, 3, minus 2, 4, B into 1, 1, minus 3, minus 2, 0, 5, C into 4, minus 1, 2, 1, minus 2, minus 3 is equal to. Now what happens? You will have the respective equations on summing up the three matrices. So you have 2A plus B plus 4C, A plus B minus C, minus A minus 3B plus 2C. So 3A minus 2B plus C minus 2A plus 0B minus 2C. 4A plus 5B minus 3C. Now, if you compare these two matrices, you will have 6 equations as a homogeneous system. So you will write a 6 by 3 matrix. So 2, 1, 4, 1, 1, minus 1, minus 1, minus 3, 2, 3, minus 2, 1, minus 2, 0, minus 2, 4, 5, minus 3. So on this, you apply the row operations, reduce into echelon form, you will get that rank of the matrix is 3. So rank of the matrix equal to number of variables. This system will have trivial solution, that is A, B, C are nothing but 0, 0, 0. Therefore, given set of matrices are linearly independent. That was the conclusion. Okay. So did you get the concept? So note down the matrix, apply the row operations on it, reduce that into echelon form and check whether the rank of the matrix is 3 or not. If it is 3, it is equal to number of variables, so it contains only trivial solution. Okay. So that's why we have started matrices first, the system of equations, because they are very useful and helpful while solving these linear dependence and independence equations. Okay. So that's all for today. Let us wind up here and we will meet on Monday with new concepts in vector spaces. So if you have any other queries, you can ask now. Any one of you. Is the discussion sufficient for you in getting the concept? Whatever we did for today, right? Thanks to all then.